Hey guys, it's Miss Markham again. We are going to work through some combined gas laws practice, but before we do that, we need to review a few things. So what we're learning to do today is how to calculate the relationships between volume, pressure, number of moles, and temperature for an ideal gas using the following formulas. So really, we're just going to focus on this last formula right here because we've already done these other two. But let's review the relationship between volume, pressure, number of moles, and temperature. So remember that temperature has a direct relationship with both volume and pressure. So whenever you heat something up, you're going to increase the volume and you're going to increase the pressure. So whatever you do to temperature also happens to volume and pressure. That's what we call a direct relationship. If you increase temperature, you also increase volume and pressure. Volume and pressure together, those relationships, or that relationship is actually an inverse relationship. So remember, when you decrease pressure, you increase volume, and vice versa. If you increase pressure, you decrease volume. So whatever you do to one, the opposite happens to the other. So remember, if temperature is involved, it is direct. And if it's not involved, then it's probably inverse. Now, as far as the number of moles goes, temperature does not affect the number of moles, but the number of moles does affect the volume and the pressure. Okay, so again, this is the equation we're going to use. This is what we call the combined gas law, which combines all of the variables that we've talked about besides moles. So we're dealing with pressure, volume, and temperature only. Okay. Okay, so just to review some of our variables, remember pressure can be found in the following units. It can be in atmospheres, it can be kilopascals, and it can be millimeters of mercury. Notice we don't have R in this equation, so we're not going to be working with the pressure constant, so we don't have to worry about that. Volume, remember, can be found in milliliters or liters, either one is fine, but temperature has to be in Kelvin. So if they give us temperature in Celsius, we'll need to convert it into Kelvin by adding 273. Should be easy peasy. Okay, so let's look at question number 1. This is in your notes. Make sure you're following along and you're writing this down and calculating with me. So it says if I initially have 4 liters of gas at a pressure of 1.1 atmospheres, what will the volume be if I increase the pressure to 3.4 atmospheres? Okay, so we're going to follow those procedures that we've been doing for the other problems. We're going to underline what they give us and figure out what variables are given in the problem. Okay, so they tell us that there are 4 liters. Now, in this equation here, we actually have a couple of volumes and a couple of pressures. So I'm going to go ahead and put volume 1 because it's the first one that they give us. They also tell us pressure. So it's the first pressure they give us, so I'm going to put P1. What will the volume be? So that's what we're looking for if I increase the pressure to 3.4 atmospheres. So they give us a second pressure, I'm going to put P2. All right, so they give us V1, they give us P1, and they give us P2, and it looks like we're looking for V2. So when we look at our equation up here, we have some extra variables that we don't need. So they don't give us temperature, so we know that temperature does not affect whatever's going on in this problem here with our gases. So we actually don't need this portion of the equation. So we're going to use P1 V1 equals P2 V2. Okay, we're going to plug our numbers in. So they give us P1, which is 1.1, and they give us V1, which is 4, and that equals P2, which they give us 3.4, and V2, which is what we are solving for, so that's our X, that's what we're looking for. So to solve this, we're going to divide by 3.4 on both sides. So you would put in your calculator 1.1 times 4, 1.1 times 4, divided by 3.4. Take a couple seconds and do that. When you calculate that out, you should get 1.29 liters. Okay. Let's go ahead and move on to number 2, example 2. A commercial airliner has an internal pressure of 760 millimeters of mercury and a temperature of 298 Kelvin at takeoff. If the temperature of the airliner drops to 290 Kelvin during the flight, what is the new cabin pressure? Okay, they give us lots of stuff here, so let's underline and figure out. What is 760 millimeters of mercury? Well, remember that's a unit for pressure. So I'm just going to put P1 since it's the first one they give us. And temperature of 298 Kelvin, so that's T1. And then it tells us that the temperature drops to 290 Kelvin, and that's T2. Okay. And then they're asking us for the new cabin pressure, which would be P2. Okay. So let's look at our equation up here. What do we not need? Well, they give us temperature and pressure, so we actually don't need volume. So we're looking at pressure and temperature. We're just going to ignore volume and plug our numbers in. So the equation we're going to use is P1 over T1 equals P2 over T2. Okay, and it looks like we're solving for P2. So let's plug our answers in. We have 760 is our first pressure, and we have 298 Kelvin. Sorry. 298 Kelvin equals pressure 2, that's what we're looking for, divided by temperature 2, temperature dropped to 290, and we just cross multiply. So you can do multiply these two together and divide by this. So 760 times 290 divided by 298, take a couple seconds, plug that in your calculator. 760 times 290 divided by 298. Okay, and that's going to give us a new pressure of 740 millimeters of mercury. Okay, so let me draw your attention to something real quick. So remember, let's figure out what's going on in this problem here. Our temperature is decreasing, right? So temperature is decreasing. What can we expect our pressure to do if temperature is decreasing? Remember, it's a direct relationship. So if temperature decreases, so does pressure. So when we look at our answer here, 740 is less than 760, so we know we did this correctly. If temperature decreases, pressure decreases, and we have mathematically proven that. So we were correct. Okay, question number 3. If a calm person with a lung capacity of 3.5 liters and a body temperature of 36 degrees Celsius gets angry, what will the volume of the person's lungs be if their temperature rises to 39 degrees Celsius? Okay, so they give us a volume. So let's put V1. They give us a temperature, so let's put T1, but there's something wrong with this temperature. Remember, we need this to be in Kelvin. So we would take 36 and we would add 273, and that would give us 309. So T1 equals 309 Kelvin. Okay, and then they give us a second temperature, which is also in Celsius. So T2, we would also need to add 273, and that would give us 312. Okay, so they're giving us volume and they're giving us temperature, and they're wanting us to find V2. So we're looking for V2. So let's come up here to our equation. Which piece do we not need? Well, it looks like we don't need pressure. So we'll mark that out, and our equation that we're going to use is V1 over T1 equals V2 over T2. And it works the same as question number 3. We're just dealing with volume and temperature this time. Okay, So let's do a little prediction before we do our calculation. What's happening to the temperature? It's saying that the temperature is rising, so T is increasing. If T increases, what should happen to V? Remember, it's direct, so our volume should actually increase a little bit. The temperature didn't increase much, but it did a little, so our volume should actually increase a little bit. So let's plug our numbers in. We have 3.5 divided by our new temperature at 309 equals, ooh, that was weird, equals, we're looking for V2, so I'm going to write that in, that's our X, divided by our new temperature we calculated, 312. Okay, again, you cross multiply, so 3.5 times 312 divided by 309, and that's going to give us about 3.53 liters. We were working with volume there. So it did increase a tiny bit. It went from 3.5 to 3.53, so we're probably correct. Okay. All right, let's work a few more, guys. Hang in there. You're doing a good job. Number 4 says a toy balloon. So go ahead and turn that page. We're on the last page of the green packet. A toy balloon has an internal pressure of 106 kilopascal